Physics is the study of the physical world, energy, matter, and how they relate. It is called the fundamental science because all other natural sciences are constrained by its laws. It generates fundamental knowledge needed for future technological advances. Science requires that quantities must be defined and measured. Things that cannot be measured, like emotions, are not science. Quantities that can be measured are called physical quantities. A complete set of units for all physical quantities forms a system of units. In 1960, an international committee agreed on a single system for the whole world known as the System International, or SI. While we can use other systems for convenience, in science we must always use SI. In the SI system, 7 physical quantities are chosen arbitrarily as base quantities, and their corresponding units are standardized. These include length in meters, mass in kilograms, time in seconds, electric current in amperes, thermodynamic temperature in kelvins, amount of substance in moles, and luminous intensity in candelas. Derived units are obtained and developed from base quantities. The number of derived quantities of interest in science and technology has no limit. Common examples include area measured in square meters, volume in cubic meters, speed or velocity in meters per second, and acceleration in meters per second squared. Pure geometrical units include the radian and stradian. A radian is the angle subtended by an arc equal to the radius. A stradian is the solid angle subtended by an area equal to the radius squared. Scientific notation is an easy way to write numbers that are too big or too small. It uses a mantissa multiplied by 10 raised to an exponent, making arithmetic operations much easier. Prefixes give proper names to powers of 10, like kilo and micro. There are also important non-SI units used globally, such as the light year, the angstrom, and the micron. When writing unit symbols, use Roman type, attach prefixes directly, and never use abbreviations. When writing unit names, start with lowercase letters, even if named after a person, and combine prefixes into a single word. Error is the doubt that exists in a measurement. Systematic errors tend to be in one direction due to design faults or bias, while random errors occur irregularly because of environmental fluctuations. The smallest measurable value is the least count error. Uncertainty is the quantification of error. Every measurement is written as a best estimate plus or minus uncertainty. This can be absolute, carrying units, or relative, represented as a percentage. When calculating, uncertainties propagate. For sums and differences, add the absolute uncertainties. For products and quotients, add the percentage uncertainties. For powers, multiply the percent uncertainty by the power. Significant figures include all accurately known digits plus the first doubtful digit. Non-zero digits, and zeros between them, are always significant. However, leading zeros are never significant. Measurement quality depends on precision and accuracy. Precision describes the exactness and consistency of a set of measurements. Accuracy describes the closeness of a measured value to the actual true value. Dimensions describe the physical nature of a quantity using brackets, such as L for length and M for mass. Dimensional analysis is highly useful to check the correctness and homogeneity of physical equations. To summarize Chapter 1, physics relies on the psi system's 7 base units. We use scientific notation for extreme numbers, must account for errors and uncertainties, and use dimensional analysis to verify formulas. Let's test your knowledge. Question 1. What is the psi base unit for thermodynamic temperature? Question 2. Is the centripetal force equation dimensionally correct? Here are the answers. Answer 1 is Kelvin. Answer 2 is true, the equation balances dimensionally on both sides. Congratulations on completing Chapter 1. Thank you for watching. Please like, share, and subscribe to PrepN5 for more physics lectures.